Load balancers are essential components in modern cloud architectures. They distribute incoming network traffic across multiple servers, ensuring no single server becomes overwhelmed. This not only improves the performance and reliability of applications, but also enhances their scalability. In the context of Microsoft Azure, load balancers can be configured to handle both internal and public traffic, depending on the needs of your application. This presentation will delve into the intricacies of configuring both internal and public load balancers within Azure, providing a comprehensive guide for Azure administrators. Load balancing is the process of distributing network traffic across multiple servers. This ensures that no single server bears too much load, which can lead to performance degradation or even server failure. Load balancers can operate at different layers of the OSI model, including Layer 4, Transport Layer, and Layer 7, Application Layer. In Azure, load balancers are used to manage traffic for applications running in virtual machines, VMs, ensuring high availability and reliability. Azure offers two main types of load balancers: internal and public. Internal load balancers are used to distribute traffic within a virtual network, VNet, making them ideal for internal applications that do not need to be exposed to the internet. Public load balancers, on the other hand, distribute traffic from the internet to VMs within a VNet. Understanding the differences between these two types is crucial for configuring them correctly based on your application's requirements. Internal load balancers are best suited for applications that require high availability within a private network. For example, an internal load balancer can be used to distribute traffic among back-end servers in a multi-tier application. This ensures that if one server fails, the load balancer can redirect traffic to other healthy servers, maintaining the application's availability. Internal load balancers are also useful for microservices architectures, where different services need to communicate with each other within a VNet. Public load balancers are ideal for applications that need to be accessible from the internet. For instance, a web application that serves users globally would benefit from a public load balancer to distribute incoming traffic across multiple VMs. This not only improves the application's performance by balancing the load, but also enhances its availability by ensuring that traffic can be redirected to healthy VMs in case of a failure. Public load balancers are also essential for scenarios where you need to expose specific services to external users. To configure an internal load balancer in Azure, you need to follow several steps. First, create a virtual network, VNet, and deploy your VMs within this network. Next, create a load balancer resource and specify that it is an internal load balancer. You will then need to configure the backend pool, which includes the VMs that will receive the traffic. After that, set up the health probes to monitor the status of the VMs. Finally, configure the load balancing rules to define how traffic should be distributed among the VMs. Configuring a public load balancer involves similar steps to an internal load balancer, with some key differences. First, create a public IP address that will be associated with the load balancer. Then, create the load balancer resource and specify that it is a public load balancer. Configure the backend pool with the VMs that will handle the traffic. Set up health probes to monitor the VM status. Finally, define the load balancing rules to determine how incoming traffic from the internet should be distributed among the VMs. Health probes are critical components of load balancers. They monitor the status of the VMs in the backend pool to ensure they are healthy and capable of handling traffic. In Azure, you can configure health probes to check the status of VMs using TCP, HTTP, or HTTPS protocols. If a health probe detects that a VM is unhealthy, the load balancer will stop sending traffic to that VM and redirect it to other healthy VMs. This ensures high availability and reliability for your applications. Load balancing rules define how traffic should be distributed among the VMs in the backend pool. These rules specify the front-end IP configuration, the backend pool, the protocol, TCP or UDP, and the port numbers for incoming and outgoing traffic. In Azure, you can create multiple load balancing rules to handle different types of traffic. For example, you might have one rule for HTTP traffic on port 80 and another for HTTPS traffic on port 443. Understanding and configuring these rules correctly is essential for effective load balancing. When configuring load balancers, security is a crucial aspect to consider. For internal load balancers, ensure that only authorized traffic within the VNet can access the backend VMs. For public load balancers, use network security groups, NSGs, to control inbound and outbound traffic. Additionally, consider using Azure DDoS protection to safeguard your applications from distributed denial of service attacks. Implementing these security measures helps protect your applications and data from potential threats. Monitoring and troubleshooting are essential for maintaining the performance and reliability of your load balancers. Azure provides several tools for this purpose, including Azure Monitor and Network Watcher. Azure Monitor allows you to track metrics and set up alerts for your load balancers, helping you identify and resolve issues quickly. Network Watcher provides diagnostic tools to monitor and troubleshoot network issues. Regularly monitoring your load balancers and addressing any issues promptly ensures the continued availability and performance of your applications. To get the most out of your load balancers, follow best practices such as regularly updating your health probes, configuring appropriate load balancing rules, and implementing security measures. Additionally, consider using auto-scaling to automatically adjust the number of VMs in your backend pool based on traffic demand. This ensures that your application can handle varying levels of traffic without compromising performance. By following these best practices, you can optimize the performance, reliability, and security of your load-balanced applications. Let's consider a case study of an e-commerce application to illustrate the concepts discussed. The application consists of a web front-end, a set of microservices, and a database. An internal load balancer is used to distribute traffic among the microservices, ensuring high availability and reliability. A public load balancer is used to handle incoming traffic from customers accessing the web front-end. Health probes monitor the status of the VMs, and load balancing rules ensure that traffic is distributed efficiently. Security measures such as NSGs and DDoS protection are implemented to safeguard the application. Configuring internal and public load balancers in Azure is a critical skill for Azure administrators. By understanding the differences between internal and public load balancers, knowing when to use each type, and following best practices, you can ensure the high availability, reliability, and security of your applications. As a next step, consider exploring Azure's advanced load balancing features, such as Application Gateway and Traffic Manager, to further enhance your load balancing capabilities. Continuous learning and hands-on practice will help you master the art of load balancing in Azure.